Hello and welcome to BBC Learning Zone, taking us through the night on BBC Two. And today we're concentrating on programmes for schools through until 6 a.m. So here's what's in store for the night. At 4 a.m, the second GCSE Bitesize Maths Revision programme, with everything you'll ever need to know about GCSE algebra and much more besides. First, it's Key Stage 3 Maths Revision, and we're getting some help today with algebra, measures, shape and space.
Hi, I'm Sally Gray. Welcome to another maths programme in the Key Stage 3 Bite-Size Revision Series. These programmes are designed to help you with your Key Stage 3 tests. And in this programme, we're going to be looking at algebra, measures and shape and space. Now remember, you can work your way through the whole menu, or you can just concentrate on the areas where you feel you need the most practice. Basically, the choice is yours. Along with the television programmes, there's also a Key Stage 3 bite-sized book and a website with more examples and questions for you to try out at your own pace. So let's kick off with algebra. In this unit on expressions and number patterns, we'll be looking at forming simple expressions, substitution and number patterns. Let's start with forming simple expressions. First, some definitions. An algebraic term is a letter that represents an unknown number, either on its own or multiplied by a number. For example, x or 3x. Now, an algebraic expression is several algebraic terms together with some or all of the arithmetic operations. That's plus, minus, multiply and divide, but no equal sign. For example, 3x minus 4y plus x is an algebraic expression. The particular letters used in an expression are not important, but understanding what the letters represent is important. For example, we can use algebra when decorating the bathroom wall with tiles. Take a look at this. This bathroom wall is crying out for a spot of retiling. But exactly what tiles we're going to use and how the different tiles can be used to form patterns is something you can decide on using computer graphics. If we decide to use 3 colours, say green, blue and red tiles, it'll help if we have some kind of order for them. For instance, suppose we had 1 green tile and 4 blue tiles to surround it in a cross shape with corners filled in with red tiles. It would look like this. Right, great tiling, but how can the pattern and its cost be expressed algebraically? To find that out, let's go to our expert.
To tile one small section of the wall with this pattern, we would need 1 green tile, 4 blue tiles and 4 red tiles. Now let's have a look at the cost in algebraic terms. 1 green tile costs X pounds. 4 blue tiles costs Y pounds each. And 4 red tiles costs Z pounds each. Now, if we want to find a total cost, what we do then is we make a simple expression. The total cost then, in pounds, we have X plus 4Y plus 4Z. Remembering, with an algebraic expression, we have terms, but no equal sign.
Right, now let's remind ourselves of some important points about algebraic expressions. An An algebraic expression is different from an equation because it doesn't have an equal sign, whereas an equation always does. The particular letters used in an expression are not important, but understanding what the letters represent is important. When a number is multiplied by a letter in algebra, the multiplication sign is left out. So rather than 4 times n, we write 4n. But if there was only one tile, t for instance, then rather than write 1t, we always just write t. So that's expressions for you. Now make sure you've got a good understanding of what we've just covered, because it's important to grasp the basics before moving on. Right, let's look at substitution now. This is where we substitute numbers for letters in the expression. And to tell us more, here's our expert.
Substitution is replacing a symbol, a letter, or an algebraic term in an expression with a value in order to find the total. So if we consider the tiling pattern that we've been looking at, we can substitute in the values for the terms in order to find the total cost. So let's consider an order form. The cost of the green tiles could come up at £1.20, for example. The blue tiles could be, say, £1.10. And the red tiles might be £1.50 each. So we can calculate the total cost for one small section of the wall by substituting the values for each of the terms in the expression. But let's just remind ourselves as to what that expression is. The total cost of x plus 4y plus 4z. So let's substitute in the values for each of the terms. The value for x is £1.20. 4 times y, which is £1.10, and 4 times the value for z, which is £1.50. So if we calculate this, we get £1.20 plus £4.40 plus 6, which gives us a total of £11.60. So that's a total cost of £11.60 for one small section of the wall.
Right, before going any further, let's recap. Substitution simply means replacing letters in an expression with numerical values to find a total. Now the final section on number patterns. Algebraic expressions can be used to explain number patterns too. Just look at the number patterns formed by these ice skaters. Watch the series of figures they make. How is this figure different from the last? And this one? What will the next figure look like, and how have the figures been formed? You might have seen the sequence made by adding one more skater to each arm of the cross. Maybe you saw each figure as one skater in the middle, with 4 lines of skaters pivoting round her. Another way of looking at it would be to say that there was one line of skaters with 2 smaller lines joined to it. And there are other possibilities. We've got just 4 figures so far, but there could be many more. What do you think the 10th figure in the sequence would look like? And how many skaters would it have? Here's one way of working it out. In each of the figures there are 4 equal arms. Each arm has 1 skater less than the figure number. So in the 10th figure, the arms will each have 9 skaters. 4 lines are 36, plus the 1 in the middle, that's 37 skaters. Alternatively, you could see each arm as 10 skaters long, the same as the figure number, but all sharing skater number 1. 4 tens are 40, but because there's only 1 skater number 1 instead of 4, we have to subtract 3. 40 minus 3 is 37. Another way of arriving at the same answer then. With a bit of thought, you can create a general rule. What would your general rule be? Well, to find that out, let's go to our expert.
For pattern number 1, we have one skater. For pattern number 2, we have one skater plus 4 others. For pattern number 3, we have one skater plus 4 more. For pattern number 4, we have one skater plus 4 and 4 more. We can think of these number patterns another way. Pattern number 1 remains the same. That's 1. Pattern number 2 is 1 plus 1 group of 4. So that's 1 plus 1 times 4. Pattern number 3 is 1 plus 2 groups of 4. 1 plus 2 times 4. Pattern number 4 is 1 plus 3 groups of 4. 1 plus 3 times 4. Now suppose we wanted to think about other number patterns for 10, 20, in fact for any number of skaters, which we could call n. Let's have a look at the patterns again. For pattern number 4, we have 1 plus 3 times 4 skaters. Now this 3 is 1 less than the number pattern. And for pattern number 3, we have 1 skater plus 2 times 4 groups of skaters. And again, this number, 2, is 1 less than the number pattern. So let's see if we can come up with a general expression. Our number pattern is 1 plus n minus 1, and we multiply that by 4. So, let's simplify this. 1 plus 4 times n minus 4. Again, that can be simplified by adding the 1 to the minus 4 to be 4n minus 3. So there is our expression, 4n minus 3, the general rule for the pattern of the skaters.
Right, now let's move on to a test question. And there are 5 parts to this question, so make sure you pause the tape and jot each one down as we go along. We're told that Jeff makes a sequence of patterns with black and grey triangular tiles. You are given pattern number 1, pattern number 2, and pattern number 3. We're told that the rule for finding the number of tiles in Jeff's sequence is 1 plus 3n. Part A. The 1 in this rule represents the black tile. What does the 3n represent? B. Jeff makes pattern number 12 in his sequence. How many black tiles and how many grey tiles does he use? C. Jeff uses 61 tiles altogether to make a pattern in his sequence. What is the number of the pattern he makes? D. Barbara makes a sequence of patterns with hexagonal tiles. Each pattern in Barbara's sequence has 1 black tile in the middle. Each new pattern has 6 more grey tiles than the pattern before. Write the rule for finding the number of tiles in pattern number n in Barbara's sequence. E. Gweno uses some tiles to make a different sequence of patterns. The rule for finding the number of tiles in pattern number n in Gweno's sequence is number of tiles equals 1 plus 4n. Draw what you think the first 3 patterns in Gweno's sequence could be. Okay, here's the lead chief marker for Key Stage 3 Maths, who's going to take us through the question from the top. First, he's going to look at the examples to understand the question fully.
Part A of the question says that the 1 in this rule represents the black tile. What does the 3n represent? Well, you can see that in each of the patterns there's always 1 black tile and either 3, 6 or 9 grey tiles. So the 3n represents the number of grey tiles, because the number of grey tiles is always a multiple of 3.
Now on to part B.
Jeff makes pattern number 12 in the sequence, and the question asks how many black and grey tiles he uses. Just like in all the previous sequences, he's going to use 1 black tile and 3 n grey tiles, where n is the number pattern. So for pattern number 12, n will be 12. Substituting for n in 3n gives 3 multiplied by 12, which is 36. So 36 grey tiles and 1 black tile.
Now this might seem like a pretty obvious thing to say, but it's always worth checking back to make sure you've answered all the parts of the question. Okay, now for the next bit. Jeff uses 61 tiles altogether to make a pattern in his sequence. What is the number of the pattern he makes?
You know that the rule for finding the number of tiles is 3n plus 1, and here this equals 61. Now you need to find the pattern number in the sequence, which means solving the equation to find n. 3n plus 1 equals 61. So 3n will be 60. And if 3n is equal to 60, then n will be 60 divided by 3, which is 20. So the pattern number is 20.
If you found this at all tricky, why not play back the answers so far and have another look? Otherwise, time to move on to Part D.
Part D of the question tells us that Barbara makes a sequence of patterns with hexagonal tiles. You're given 3 pattern numbers. You're told that each one has a black tile in the middle and 6 more grey tiles. You're then asked to write the rule for finding the number of tiles in pattern number n in Barbara's sequence. Now, pattern number 1 has 1 black tile plus 6 grey tiles. Pattern number 2 has 1 black tile plus 12 grey tiles. And pattern number 3 has 1 black tile and 18 grey tiles. It seems that any pattern number has 1 black tile and 6 times the pattern number of grey tiles. See, pattern number 1 has 6 multiplied by 1, that's 6 grey tiles. Pattern number 2 has 6 multiplied by 2, that's 12 grey tiles. And pattern number 3 has 6 multiplied by 3, that's 18 grey tiles. So pattern number n will have 1 black tile, like all the others, and 6 multiplied by n grey tiles. Therefore, the rule for finding the number of tiles altogether in pattern number n is 1 plus 6n.
And now for the final part of the question.
Finally, you're given Gweno's sequence of patterns with the number of tiles being 1 plus 4n. You're asked to draw what you think the first 3 patterns in Gweno's sequence could be. There is a hint from the rest of the question. Jeff's pattern was 1 plus 3n for triangles, and Barbara's pattern was 1 plus 6n for hexagons. Gweno's is 1 plus 4n. Triangles have 3 sides. Hexagons have 6 sides, so it looks like Gweno's pattern may be squares, which have 4 sides. The 1 tells us that the number of black tiles in every pattern is 1, and the 4n tells us that the number of grey tiles in every pattern is 4 multiplied by the pattern number. So for pattern number 1, you can draw 1 black tile surrounded by 4 multiplied by the pattern number 1, so that's 4 grey tiles. For pattern number 2, you can draw 1 black tile again, and 4 multiplied by the pattern number 2, so that's 8 grey tiles. And finally, for pattern number 3, draw 1 black tile and 4 multiplied by pattern number 3, so that's 12 grey tiles.
So, how'd you get on there? Well, if your answers didn't match ours, then why not go back and give it another bash? Otherwise, let's recap, shall we? always look carefully at the rule for a number pattern and make sure you understand what each number and each letter in the rule is telling you. Right, that's it for this unit. If you want more questions and exercises on expressions and number patterns, you can always refer to the Bitesize book and, of course, our website. Right, we're moving on now to algebraic equations. While algebraic expressions had lots of algebraic terms, together with arithmetic operations, an algebraic equation always has an equal sign and at least one letter that has an unknown numerical value. To solve an equation, we need to discover what that numerical value is.
Let's take the example 3x equals 9. What we're interested in is what x is. Now it's easy to see 3 times 3 equals 9. So then x equals 3. There's our answer. It's helpful to remember that an equation can be thought of as a balance.
In other words, any mathematical operation, addition, subtraction, multiplication or division, performed on one side of the equation must also be performed on the other side to make the equation balance and to make the equal sign still work. Here's an example.
Let's take an example where all of the numbers are known. 4 plus 7 equals 11. Now, if we add 5 to one side of this equation, if we remember our rule, we also need to add 5 to the other side of the equation to ensure that the equal sign is still correct. Now what does that give us? 4 plus 7 is 11 plus 5, which is 16. 11 plus 5 is 16. So the equal sign is still true. Okay, let's continue. 4 plus 7 plus 5. But now, let's divide this by 2. Remembering our rule, what's done on the left-hand side must also be done on the right-hand side of the equation. So we need to do the same here. And the answer is 16 divided by 2 is 8. And again, 16 over 2 is 8.
Right, let's recap before moving on. Any mathematical operation that's addition, subtraction, multiplication or division performed on one side of the equation must also be performed on the other side. Now let's see how this rule helps us solve equations.
Let's take the example x plus 9 equals 16. Now we know this is an equation because it has an equal sign. What we're asked to do is to solve this equation to find a numerical value for x. Okay, so we have x equals an unknown number. What have we got? X plus 9. So to get x on its own, we've added 9, so let's subtract 9. X plus 9 minus 9 will go to 0. What we do on the left-hand side, we also have to do on the right-hand side. So we subtract 9 from this side. So we have 16 minus 9. So the expression now, x equals 16 minus 9, so x equals 7. The good thing about equations is that we can substitute this value into the original expression to see if we've done it correctly. 7 plus 9 equals 16. It's correct.
Right, what about another equation?
Let's take this example. X minus 11 equals 13. Now what we want to do is to find x on its own. At the moment, x has 11 subtracted from it. So what we need to do is to add 11 so that this becomes 0. Minus 11 plus 11 gives 0, leaving x on its own. Now remembering our rule, what's done to the left-hand side of the equation must also be done on the right-hand side of the equation. So 13 plus 11. What does this give us? 13 plus 11 x equals 24. Now the good thing about this is we can substitute the value that we have into the original equation to check if we've done this correctly. 24 minus 11 equals 13. Yes, it's correct.
So far, the equations have been quite straightforward, really. But we can make them a little bit more complicated by including multiplication or division and addition or subtraction. Here, a second rule comes into play. Always deal with the pluses and minuses first.
Let's consider this equation. 4n minus 7 equals 5. What we're aiming for is n equals a number. First of all, let's find 4n. In order to do that, we've got 4n minus 7. So let's add 7 to make this 0, which will leave us with just 4n. Okay, what's done on the left-hand side of the equation must also be done on the right-hand side of the equation so that our equal sign still works. So now, we add 7 to the right-hand side of the equation to give us 5 plus 7. What do we have now? 4n equals 12. Right, we've got 4 times n. To get n on its own, we divide by 4, remembering a number divided by itself equals 1 or 1n. So 4n over 4. Doing the same to the right-hand side of the equation gives us 12 divided by 4. So what does that give us? N equals 3. We can take this value of n and substitute it in the original equation to see if we've done this correctly. So we have 4 times 3, where 3 is n, minus 7 gives us 5. It's correct.
In the last unit, we were looking at tiling a bathroom. Well, if the cost of tiling changes and there are bargains to be had, algebraic equations can come in very handy here too. So let's go to our expert.
Suppose the cost of the tiles to tile one small section of the wall at the end of the bath with 2 green tiles, 8 blue tiles and 8 red tiles comes to £23.20. And if I've already agreed with my neighbour to pay him for doing this for me, a labour cost of £15. So to tile this small section of the wall, the cost will be £38.20. But my budget is already fixed at £30. So how do we get round this problem? Well, I've got 2 choices. I can either lose the labour cost by doing the work myself, or I can use cheaper tiles. Now, my DIY skills are such that I think it might be better if I ask my neighbour to do the job for me. So let's investigate cheaper tiles. Now, white tiles cost £0.75 each. In problems like this, it's better to stick to 1 unit. It's not pounds or pence, just stick to 1. So we'll stick to pounds. Right, so what I'm interested in finding then is how many tiles I can afford to buy with a budget of £30 and a labour cost of £15. Right, let's represent the number of tiles using a symbol W. W is the number of tiles needed. So let's come up with an equation. 0.75W plus £15 equals £30. We can simplify this and represent it like this. 0.75W plus 15 equals 30. Now, to get 0.75W on its own, we can see it has 15 added to it. So let's subtract 15, bringing that to 0 to leave 0.75W on its own. If we remember our rule, what's done to the left-hand side of the equation must also be done on the right-hand side of the equation. So we need to subtract 15 over here. So that's 30 minus 15, so that the equal sign still works. Right, what do we have now? 0.75W equals 15. To get W on its own, it's multiplied by 0.75, if we divide by 0.75, we'll have W, because a number divided by itself gives 1, in this case 1W, or just W. Doing the same on the right-hand side of the equation, 15 divided by 0.75, to give us W equals 20. We can put this value into our original equation to check that we've done it correctly. 0.75 times 20 plus 15 equals 30. Calculating this gives us 15 plus 15 equals 30. We can see that we've done it correctly.
Now, if you found that a bit tough, don't worry, because you're not the only one. Here are some students with a few of their good tips on algebra.
Equations often look scary, but once you simplify them, they're really easy.
A good way to think of an equation is to think of it as a seesaw. What you do to one side, you have to do to the other to keep it balanced.
A rule for equations is you must do addition and subtraction before multiplying and dividing.
The letters in an equation stand for the numbers. It's our job to find out which numbers the letters stand for.
Right, time now to move on to a test question. And this one's divided into 2 parts, so you'll need to write it all down. Class 9H were playing a number game. Ellen said, multiplying my number by 4 and then subtracting 5 gives the same answer as multiplying my number by 2 and then adding 1. Part A says that Lena called Ellen's number x and formed an equation 4x minus 5 equals 2x plus 1. Solve this equation and write down the value of x and show your workings. Then we're told Alid said that multiplying my number by 2 and then adding 5 gives the same answer as subtracting my number from 23. Part B says to call Alid's number y and form an equation. Work out the value of Alid's number. And take a few moments to pause the tape and work these 2 parts out yourself. Okay, now for the answers. And who better to tell us than the chief marker himself? And he's going to answer each part one at a time. Part A says, work out the value of x and show your workings.
You have 4x minus 5 on one side and 2x plus 1 on the other. In order to solve it, you're aiming for the letter equaling some number. So you need to get x on its own on one side of the equation. Start by getting all the x terms onto one side. Do this by subtracting 2x from the right-hand side, so that there are no x's there. So you have 2x minus 2x, making 0, plus 1. Applying the rule that you must perform the same operation on both sides of the equation for the equals still to work, you also need to subtract 2x from the left-hand side, making 4x minus 2x minus 5. Now you have 4x minus 2x, which leaves 2x minus 5 equals 1. Get the 2x on its own now by adding 5. Add 5 to the left-hand side, and the minus 5 add 5 leaves just the 2x. Now, performing the same operation on the other side of the equation, you have 1 add 5. So 2x equals 6. Now divide both sides by 2, and you're left with x equals 3. A quick substitution in Lena's equation, 4x minus 5 equals 2x plus 1, will tell you if you are correct. First of all, if x equals 3, the left-hand side, 4x minus 5, is 4 multiplied by 3, that's 12, subtract 5, which is 7. And the right-hand side, 2x plus 1, is 2 multiplied by 3, that's 6, add 1 is also 7, so the equation does balance.
OK, now for part B.
Going by the statement you're given, taking the number y, multiplying by 2 and adding 5 would be 2y plus 5. This gives the same answer as subtracting the number from 23. So take 23 and subtract y. 23 minus y. So the equation is 2y plus 5 equals 23 minus y. Then you're asked to work out the value of Alid's number. So this time you're looking to get y equals some number. Get rid of the subtract y on the right-hand side by adding y, which of course means adding y to the left-hand side too. That leaves you with 2y, add 5 equals 23, subtract y, add y. So that's 3y, add 5 equals 23. Now, aiming to get the 3y on its own, subtract 5 from both sides, leaving 3y, add 5, minus 5 on that side, equals 23 minus 5 on that side. So that's 3y equals 18. Now there is a 3 multiplying the y, so divide both sides by 3 and you have y equals 6. So Alid's number is 6. A quick check in the original equation then. 2y plus 5 equals 23 minus y. If y equals 6 on the left-hand side, you have 2y add 5 equals 2, multiplied by 6, that's 12, add 5 equals 17. On the right-hand side, you have 23 minus y, so that's 23 minus 6, which is also 17. You know you are correct.
OK, now for some key points. Any mathematical operation that's addition, subtraction, multiplication or division performed on one side of an equation must also be performed on the other side of the equation for it still to be correct. Always deal with any additions and subtractions in equations first, then move on to dividing or multiplying. Right, that's the end of this unit, and to make sure you're happy with your equations, it might be a good idea to go back to any questions you found a bit tricky and work them through again one more time. And if you want to find out more, why not check out the Bitesize book or log on to our website. Right, now on to measures, and we're going to kick off by looking at a unit on perimeter and area. The perimeter of a two-dimensional shape is the distance all the way around the outside. So for instance, the perimeter of this square would be 4 meters, because each of the sides is 1 meter long. And the perimeter of this kite is 2 meters along this side, 2 meters along this side, then 1/2 meter along this side, and 1/2 meter along this one. That's a total of 5 meters, a perimeter of 5 meters. Now, what about finding the perimeter of a circle? Well, for a start, let's check through the vocabulary we use when describing circles. The distance all the way around a circle is called the circumference. The diameter is the distance from one point on the circumference to another, going through the center of the circle. And the radius is the distance from the circumference to the center of the circle, or half the distance of the diameter. Now, to find a circle's circumference, you first need to know either its diameter or its radius. So as the diameter is any straight line from any point on the circle through the center to any other point on the circle, we might measure across here, or across here, or here. The radius is any straight line from any point on the circle to the centre of the circle, and we might measure it here, here, or perhaps here. There's a way of calculating the circumference of a circle. To do this, we multiply the diameter by a special number or a constant, and this number is approximately 3.14. Now I say approximately because it's actually 3.141592653589793238462 and so on. In fact, this decimal goes on and on forever and ever with no repeating. So we can never actually write the entire number down. Instead, mathematicians just call this number by the simple name pi, which is a Greek letter. And it's important to remember that whatever the size of the circle, pi always remains the same. This is true of all circles, whatever their size. It's true of all these different circles on the screen, and it would be true if you drew a circle round the Earth and divided the circumference of the Earth by the diameter of the Earth. The result would be the same, pi. For some examples of finding the circumferences of circles, let's go to our expert.
If I want to find the circumference of this circle, the first thing I notice is that the diameter is 11 centimetres. So I'm going to use a formula to help me work out the circumference. The formula for circumference is pi multiplied by the diameter. Now pi we can approximate to be about 3.14. And we multiply that by the diameter of this circle, which is 11. I'm just going to work that out on my calculator now. That gives us 34.54 centimetres. Suppose I don't have a calculator handy. How can I work out the circumference of this circle? Now I've got a radius of 2.5 centimetres. Now that doesn't help me because the formula you need to know the diameter. So let's try and work out the diameter. 2.5 times 2 gives you the diameter, which is 5. Now, I haven't got a calculator, so I'm going to approximate what pi is. I'm going to round it down to 3, and we multiply it by the diameter, which is 5. Let's work that out. 3 times 5 gives you a circumference of 15 centimetres.
Okay, let's summarise what we've done so far. The perimeter of a flat shape is the distance all the way around the outside of the shape. The perimeter of a circle is called the circumference. The diameter is any straight line from any point on the circumference through the centre to any other point on the circle. The radius is any straight line from any point on the circumference to the centre of the circle. Diameter equals 2 multiplied by the radius. The circumference equals pi times diameter. Unless told otherwise, round pi to 3.14. But if a question asks for an approximate circumference, then you can round pi to 3. Okay, time for a test question now, and it's in several parts, so you might like to jot them down. John has these 8 lengths of string. 3 lengths of 1 centimetre, 1 length of 2 centimetres, 2 lengths of 3 centimetres, a 4 centimetre length and a 5 centimetre length. Part A says that John uses his lengths of string to make a rectangle with a perimeter of 14 centimetres and asks us to show how John can make a different size rectangle also with a perimeter of 14 centimetres. Part B. John makes the letter J with his lengths of string. Find the lengths X and Y and the perimeter of the letter J. Part C. John uses his 2 centimetre length of string and his 4 centimetre length of string to make a circle of circumference 6 centimetres. What is the diameter of John's circle? So how'd you get on there? Well, to go to the answers, let's go to the lead chief marker himself. Part A asks you to show how John can make a different size rectangle with a perimeter of 14 centimetres.
In maths, it always pays to try and work logically. You know that a rectangle has two pairs of sides of equal length. So begin with a rectangle with a pair of sides of length 1 centimetre. That would give you a rectangle like the one John has already made, with two sides 1 centimetre and two sides of 6 centimetres.
Okay, what about a rectangle with a pair of sides measuring 2 centimetres?
You could use the 2 centimetre length of string on one side and two 1 centimetre lengths of string on the other side. That's 4 centimetres of the perimeter already. To make a perimeter of 14 centimetres, you would need the other pair of sides to add to 10 centimetres, so they need to be 5 centimetres each. So you could use the 5 centimetre length of string, the 4 centimetre length of string, and the last 1 centimetre length of string. Just to check, perimeter equals 2 centimetres plus 5 centimetres plus 1 centimetre plus 1 centimetre plus 1 centimetre plus 4 centimetres, and that comes to 14 centimetres in total. That's another solution.
Okay, what about a rectangle with a pair of sides that measure 3 centimetres?
This time you could use a pair of 3 centimetre lengths of string on two sides. That makes 6 centimetres of the perimeter, leaving another 8 centimetres to make a perimeter of 14 centimetres. So the 4 centimetre length of string could go here, and the final 3 centimetre length with a 1 centimetre length here. Check that works. Perimeter equals 3 centimetres plus 4 centimetres plus 3 centimetres plus 1 centimetre plus 3 centimetres, totalling 14 centimetres. That's another solution.
What about part B? Find lengths x and y and the perimeter of the letter J.
You can see from the J shape that the x length plus the length of 1 centimetre make 4 centimetres. See this length across here. So x must be equal to 3 centimetres. And you can also see that the y length plus the length of 3 centimetres make 5 centimetres. See this length down here. So y must be equal to 2 centimetres. Now work around the outside of the J shape to find the perimeter, beginning here. Perimeter equals 1 centimetre plus 5 centimetres plus 4 centimetres plus y, which is 2 centimetres, plus x, which is 3 centimetres, plus 3 centimetres. That totals to 18 centimetres.
Part C. John uses his 2 centimetre length of string and his 4 centimetre length of string to make a circle of circumference 6 centimetres. What is the diameter of John's circle?
When starting a mathematics problem, it's a good idea to write down what you know about the question. In this case, you know that the circumference is 6 centimetres. You also know that the circumference of a circle equals pi multiplied by the diameter. So put what you know in the formula. The circumference is 6, so the diameter is 6 divided by pi, giving an answer of 1.91 centimetres.
Right, we've tackled perimeter, so let's move on. Now for area. The area of a two-dimensional shape is the amount of space the shape covers, and the units of area are called square units. They may be millimetres squared, centimetres squared, or metres squared. For more information, here's our expert.
Right, let's look at this square. It's got a length of 1 centimetre and a width of 1 centimetre. Any square with these dimensions 1 by 1 is called a unit square, whether you're measuring in centimetres, millimetres, kilometres or metres. So the area equals 1 centimetre squared. And we write squared by putting a little 2 above the centimetre sign, or you can write it as A equals 1 centimetre squared. Here we've got a rectangle. This rectangle has got an area of 1, 2, 3, 4, 5, 6. So the area of this rectangle equals 6 centimetres squared. Don't forget to put your 2 there to show that it is centimetres squared. Another way of writing it is A equals 6 centimetres squared. Let's move on to a different shape now. Now let's use millimetres. First thing to consider is to look at this square here. You can either call that 1 centimetre squared or 10 millimetres squared. So here we would have either 1, 2, 3 centimetres squared or 10, 20, 30 millimetres squared. Now that we know that, let's carry on and count the squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now if we were to write the area in centimetres, it would be 24 centimetres squared. If we were to write the area in millimetres, it would be 2,400 millimetres squared. Right, let's try and work out the area of this triangle now. First thing we do is look at the whole square, because a triangle is actually half of the square. Right, let's count all the squares first. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the area of the square equals 16 centimetres squared. Now we want to find half of that to find the area of the triangle. Half of 16 is 8. So the area of the triangle equals 8 centimetres squared. Right, let's move on to a parallelogram now. First thing we do is we count the number of whole squares that we've got. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 whole squares. Now let's count the part squares. It's 1, 2, 3, 4, 5, 6. Now if we put those together, in this case they add up to 3 whole squares. So those 3 whole squares plus the 9 we've already got gives us 12. So the area of this shape equals 12 centimetres squared.
The area of any shape can be estimated by dividing it into smaller parts and counting them. It's often easiest to divide the shape into small squares. Take a look at this real-life example which involves measuring an awkward shape like a leaf.
Anna is measuring a leaf so she can calculate the amount of carbon dioxide it absorbs per minute. She'll do this for a sample of about 10 leaves to compare the efficiency in different parts of the canopy. She needs to know how much carbon dioxide each leaf absorbs in relation to its surface area, so the area needs to be estimated. How would you do this? How would you estimate the area of a leaf? When we measure a line, we fill it with units of length which we can count. This line is about 4 units long. When we measure a surface, we must cover it completely with units of area, all the same size, so each covers the same amount of surface. These pieces are all the same size and they fit together without gaps, but you could hardly say the area was 8 birds. You could use hexagons or possibly triangles, but it's easiest to use squares. We can find the area of this shape by counting the number of squares which cover it. Let's start with the whole squares. Up to 28. But we still haven't found the whole area. Some squares lie partly inside and some partly outside the boundary. How would you deal with these? One way is to assume that the boundary squares which are more than half full make up for the squares which are less than half full. So we could estimate the number of whole squares by counting all the boundary squares and dividing that by 2. That equals 19. This gives a total area of 19 plus 28, 47 squares. In the laboratory, Chris puts a dot in the whole squares. These squares are 1 centimetre each way, so they have an area of 1 square centimetre. She does the same for the number of part squares and divides this by 2 to give an estimate of the total number of squares that the leaf covers. So this leaf has an area of 37.5 square centimetres, and that seems to be a fairly representative size. With this information, she can estimate the amount of carbon dioxide absorbed and the amount of oxygen given off for the whole of the canopy, indeed, for the whole of the rainforest. Trees are vital for our survival, and by using the data collected, scientists are able to advise countries on planting species of trees and planning forest development in such a way that they won't run out.
The area of a circle can also be estimated. Take a look at this. What is the area of this shape? A circle. We can break it up into squares. It's about 3/4 of the area of the square that surrounds it. The side of the square is the diameter of the circle. Alternatively, we can cut the circle into equal sectors. This shape is, well, nearly a rectangle. Half the circumference of the circle roughly forms the length or one side of the rectangle, and the height of each of the segments is approximately the radius of the circle. But we can be more accurate than this when finding areas. The area of a rectangle or square can be found by multiplying the length by the width. Look at this rectangle. Let's write down its dimensions. Length equals 9 centimetres. Width equals 7 centimetres. Area equals length multiplied by width. So the area equals 9 multiplied by 7. That's 63 centimetres squared. The area of a triangle is base length multiplied by the height divided by 2. In this triangle, its base length equals 5 centimetres and height equals 8 centimetres. Area equals base multiplied by height divided by 2. That's 5 multiplied by 8 divided by 2, or 40 divided by 2. So area equals 20 centimetres squared. The area of a parallelogram is base length b times height h, or b times h. Let's take another look at that triangle. Let's copy it, rotate the copy through 180 degrees and join it to the original triangle. Now we've made a parallelogram. The parallelogram should have an area that's twice the area of the original triangle. The base of the parallelogram is 5 centimetres and its height is 8 centimetres. Its area is base multiplied by height. That's 5 multiplied by 8, which is 40 centimetres squared. That's indeed twice the area of the triangle. Finally, the area of a circle is pi multiplied by the radius squared, which means multiply by the radius, then by the radius again. So this circle with a radius of 3 centimeters has an area of pi, or 3.14, multiplied by 3, multiplied by 3 again, which comes to 28.3 centimeters squared. Now, although you'll be given most of the formulae at the front of the test paper, you should still make sure that you're familiar with them and that you know how to use them. So why not rewind the tape and check that you can calculate the areas of the shapes we've just shown you using the correct formulae. Otherwise, you can move straight on to this next test question. Part A. The diagram shows a rectangle 18 centimeters long and 14 centimeters wide. It's been split into 4 smaller rectangles. Write the area of each small rectangle on the diagram. One has already been done for you. What is the area of the whole rectangle? What is 18 multiplied by 14? Part B. A circle has a radius of 15 centimeters. What is the area of the circle? You have to write your answer in centimeters squared. Show you're working. So, how did you fare? Well, let's work through the question part by part. For part A, you're asked to find the area of each small rectangle on the diagram. Now find the area of the whole rectangle. And finally, you're asked what 18 times 14 is.
You are shown a rectangle 18 centimeters long and 14 centimeters wide, split into 4 smaller rectangles, and you are asked to find the area of each small rectangle on the diagram. The question says that one has already been done, so look at that first. It is this rectangle here, which is 10 centimeters long and 4 centimeters wide. You find the area of a rectangle by multiplying length by width. So that is 10 by 4, and that's how they got the 40 square centimeters here. Now look at the rectangle above it. In fact, it is a special rectangle because it has a length of 10 centimeters and a width of 10 centimeters. So it's a square. So its area is 10 multiplied by 10. So that's 100 square centimeters. Now look at the rectangle next to that square. That has a length of 8 centimeters and a width of 10 centimeters. So its area is 8 multiplied by 10. So that's 80 square centimeters. Finally, the rectangle below that has a length of 8 and a width of 4. So its area is 8 multiplied by 4, which is 32 square centimeters. Now, remember that area measures space covered, so each of these areas tell us the space covered by each of these small rectangles. So to find the area of the whole large rectangle, you can just add up the areas of the smaller rectangles that make up the large one. So that's 40 square centimeters, plus 100 square centimeters, plus 80 square centimeters, plus 32 square centimeters. And that comes to 252 square centimeters. And finally, you are asked what 18 multiplied by 14 is. Notice that the whole large rectangle has length 18 centimeters and width 14 centimeters. So its area is 18 multiplied by 14, and we already know that its area is 252 square centimeters. So 18 multiplied by 14 is 252.
For part B, you're asked to calculate the area of the circle.
This circle has a radius of 15 centimeters, and you need to calculate its area, not forgetting to show your working. Write down what you know first of all. You know the radius equals 15 centimeters. The formula to find the area of a circle is pi multiplied by the radius squared, which means pi multiplied by the radius multiplied by the radius again. So the area of this circle is pi multiplied by 15 multiplied by 15 again. Your calculator should give 706.5 square centimetres. If your calculator does not have a pi button, use the approximation 3.14 for pi.
Right, now let's summarise this section. Perimeter is always measured in centimetres, metres or millimetres. Use pi when finding the circumference or area of circles. Area measures the surface covered. Find the area of a shape by counting squares or using a formula. Area is always measured in square units. Find the perimeter of a shape by working all the way around the shape, adding every length to find the distance around the outside. And don't leave any lengths out. Well, that's it for this unit on perimeter and area. You can find more information and practice questions in the Bitesize book and on our website. And if you want to go over anything, just rewind the tape and play it again. The volume of a shape is the amount of space the shape occupies. The units of volume are called cubic units and are usually millimetres cubed, centimetres cubed or metres cubed. This is a cube with width 1 centimetre, height 1 centimetre and depth 1 centimetre. Any cube of dimensions 1 by 1 by 1, be it centimetres, millimetres, metres or kilometres, is called a unit cube. This cuboid is made up of 12 of the centimetre cubes. So its volume is 12 centimetres cubed, written as centimetres with a small 3 up here. This cube is made up of 125 centimetre cubes. So we say its volume is 125 centimetres cubed. So in other words, finding the volume can be worked out by counting cubes. Take a look at this clip.
Imagine these cubes are blocks of ice. There are 5 layers. And in each layer, there are 20 rows. If we break up the rows still further, we can see that there are 10 cubes in each row. So in one layer, there are 20 rows of 10 cubes. Altogether, there are 200 cubes of ice. There are 5 layers of 200 cubes, giving us a total of 1,000 cubes of ice.
But we can't always work out volume by counting cubes. When things get more complicated, we use formulae. Here's our expert.
To find the volume of this cuboid, we can count the number of squares we've got here, these centimetre squares. We've got 1, 2, 3, another 3, another 3, and another 3. That gives us 12. Now we mustn't forget the ones that are underneath. We've got 12 more there. So 12 and 12 is 24. So the volume of this cuboid is 24 centimetres cubed. Now, an easier way to do that would be to use a formula. The formula for finding out the volume of something, whether it be a cuboid or a cube, is length times width times height. So let's use the formula to work out the volume of this cuboid again. So the length is 4. 1, 2, 3, 4. Let's write that here. 4 multiplied by the width, which is 1, 2, 3, multiplied by the height, which is 1, 2. Now if we work that out, 4 times 3 is 12, 12 times 2 is 24. And we write that as 24 centimetres cubed.
Okay, let's now look at a practical application of volume.
This is the London Aquarium. 3 floors of gigantic fish tanks filled with marine wildlife from all over the world. Sharks, jellyfish, piranha, in fact almost every type of fish that you can't get down your local chippy.
the aquarium has 41 tanks containing 350 different kinds of marine life, and that means an awful lot of water. The designers of the aquarium had to know exactly how much, because any liquid has a weight as well as a volume. They had to be sure that the building could support the weight of the tanks. But to find out, they first had to calculate the volume.
So Brian, how do you work out how much water you're going to need to fill this particular tank?
This is a fairly easy calculation for a regular shaped cuboid such as this tank here, where we would multiply the length of the tank by the width of the tank and the depth of the tank, and that will give us the volume of water that we have in this tank.
From experience, Brian can also use some shortcuts to estimate volumes of water. For example, he knows that 1 metre cubed, like this, 1 metre cubed, holds 1,000 litres of water, but not all the tanks are cuboid.
There are all sorts of shaped tanks here, but by dividing them up into simple shapes like rectangles and triangles, Brian could calculate their volumes. He's worked out that the aquarium has 2.5 million litres of water. That's enough to fill 10,000 baths. And with that information, he worked out how heavy the water was. This was fairly easy because he knew that 1 litre of water weighs 1 kilogram. So 10 litres would weigh 10 kilograms, 100 litres, 100 kilos. So the 2.5 million litres in the aquarium weighed 2.5 million kilograms, or 2,500 tons of water, heavier than 200 buses. And the designers found that the only way to hold that amount of water was to build the tanks directly onto the foundations of the building. Any other way, and the tanks would have fallen through the floor.
Right, let's summarise now what we've just checked through. The volume of a solid is the amount of space the solid takes up. The units of volume are called cubed units. Volume can be worked out by simply counting the unit cubes. The volume of a cuboid can be found by multiplying the length by the width by the height. Okay, on to a test question now. This cuboid is made from 12 small cubes. Part A asks you to write how many small cubes there are in this cuboid. Part B. This shape is made with 2 cuboids. Write how many small cubes there are in this shape. So how did you get on there? Well, let's take the answers each part at a time.
First of all, look at the first cuboid. You are told this cuboid is made from 12 small cubes. You can tell that because you can see 1, 2, 3, 4, 5, 6 cubes on the top, and then there are clearly 6 cubes on the bottom too, making 12 cubes altogether. Now look at part A. You are shown this cuboid and asked to write how many small cubes there are in the cuboid. This time we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 cubes on this top row, and there are another 15 underneath. So that's 30 cubes altogether.
Part B. This shape is made with 2 cuboids. Write how many small cubes there are in this shape.
Try to identify the 2 cuboids. There is one here, and there is also this one here. Look at this cuboid first. You can see that this one is made up of 1, 2, 3, 4 on the top and 4 underneath. That's 8 cubes there. Now look at the other cuboid. You can see that this is made up of 4 cubes along here and another 4 alongside. That's 8 cubes on the top row, then 8 underneath. That makes 16 cubes. Adding the number of cubes in both cuboids together, 8 plus 16, that's 24 cubes in total.
Wow, that's the end of this unit on volume. But don't forget, there are more questions and exercises for you to practice in the book and on our website. Moving on to shape and space now. We're going to revise angles, symmetry, congruence and translation, and two-dimensional shapes and three-dimensional solids. First, let's kick off with angles. An angle is measured in degrees, and it measures a turn or rotation. But different angles have different names. And you'll know this one, it's called a right angle or 90-degree angle. Angles measuring from 0 to 90 degrees are called acute angles. Angles measuring from 90 to 180 degrees are called obtuse angles. And angles measuring from 180 to 360 degrees are called reflex angles. Okay, now we've reminded ourselves of the basics, let's get down to the practical part, measuring and drawing angles. And to kick us off with measuring angles, here's our expert.
Okay, let's measure this acute angle now. Right, first thing you have to do is find the line that says 0 on your protractor or your angle measurer. You place that on a line on your angle, like so. Make sure that it is straight, okay? And then you follow your scale around. Make sure that you're reading the correct scale, the one on the inside here. So if I follow it round and stop, we can see that the angle is about 59 degrees. So let's write that in. 59 degrees. Remember what I said at the beginning, it's an acute angle. So already we know that it's got to be no more than 90 degrees. If your measurement is more than that, then you know you've gone wrong somewhere. So always make sure that you know what sort of angle you're looking for. Now, one thing to remember is that when you're measuring your angles, it's okay to be 1 degree more or less than the actual angle measurement. You will still get a mark for that.
Okay, now how about drawing angles accurately?
This time I'm going to draw an obtuse angle, which you should know is more than 90 degrees but less than 180. Okay? Now I'm going to mark a point on my horizontal line that I've got here, anywhere on my line. Okay? Now this point tells me where I should start measuring from and where I should put my protractor. So I'm going to place the centre point of my protractor where I've made that mark. Make sure that your protractor is straight. Okay, hold it still. Now this time I want to draw an angle of 115 degrees. So make sure that you're reading the correct scale. Follow your scale around until you get to your chosen number. 110, 120. I want midway, I want 115. So I follow the scale and I draw a little mark there to show me where to start drawing from. Now I'm going to join up the two dots that I've made using a ruler. Hold your ruler still. Draw a straight line, joining the two dots. Now, hopefully this angle here should measure 115 degrees. Let's just test that. So I place my protractor on the centre point, make sure it's straight, hold it still, and then follow the scale around 100, 110. Make sure it's straight the whole time. And here we go, 115 midway. Okay, so I've now drawn an angle of 115 degrees.
When drawing or measuring an angle, always look at it to see if it's acute, obtuse or reflex. This will help you to assess if you have drawn or measured it correctly. Draw and measure angles with a sharp pencil and as accurately as possible. You'll lose marks for being more than 1 degree out. Okay, now for some more facts you need to know when you're calculating angles. A complete term makes a circle and is 360 degrees, so angles A and B add to 360 degrees. A half turn makes a straight line and is 180 degrees, so angles A and B add to 180 degrees. A quarter turn makes a right angle and is 90 degrees, so angles A and B add to 90 degrees. Right, here are some important points to take in. Supplementary angles make a straight line. Supplementary, straight, both beginning with an S there, that's easy to remember. Conjugate angles make a complete turn, and complementary angles make a quarter turn. Okay, so 3 angles to take in there. Let's now see how this helps us calculate angles.
Right, here we've got a right angle. A right angle is made up of 90 degrees. Now we have to find angle A. We've already got 37 degrees here. This is a complementary angle. That means that 37 and A must add up to 90 degrees. So let's write 90 degrees minus the 37 degrees that we've already got. That equals 53 degrees. So A equals 53 degrees. Okay, and that is called a complementary angle. Now let's move on to a different one. Right, this time we want to find angle B. This is a conjugate angle. That means that these figures have to add up to 360 degrees. We've already got 320 degrees. Now we need to find B. So let's take 360 degrees minus the 320 that we've already got, and that will leave us with the answer for B, which is 40 degrees. So angle B equals 40 degrees. Okay, now let's move on to the next one. This time we've got a straight line. A straight line always adds up to 180 degrees. We've already got 130 degrees. We need to find angle C. Now this is a supplementary angle, which means both figures must add up to 180.
So we have 180 degrees minus 130 degrees. That equals 50 degrees. Therefore, angle C equals 50 degrees. Let's look at vertically opposite angles now. The thing to remember about these is that they are equal, that they are the same. So if we start with angle A, if we look here, 60 degrees. Therefore, its opposite angle of A must also equal 60 degrees. Now let's look at angle B. It's vertically opposite to 120 degrees. Therefore, angle B is also worth 120 degrees. Now, just to check that we've got that right, angles on a straight line should add up to 180 degrees. Let's do that really quickly. 120 plus A, therefore 120 plus 60 is 180 degrees. And let's do it with the other one quickly. 60 plus B, B, which is 120 degrees, equals 180 degrees. Now, as we already know, the corners of a triangle add up to 180 degrees. So if I took out this angle, and this angle, they should add up to 180 degrees. To prove that, let's put them on a straight line to see if they do add up to 180. I've taken the angle, put it here, taken the other angle, put it here, and taken the third angle from the triangle and put it here. And you can see that they all add up on a straight line to give you 180 degrees.
So far, so good. Let's move on now to angles between parallel lines. Parallel lines are lines that always have the same distance between them. This means that they never meet, a bit like a railway track. Parallel lines can be part of a shape, like a parallelogram, a rhombus, or a trapezium, and they're marked by arrows on them. Now, if parallel lines are cut or intersected by a straight line, a transversal, then it creates the following angles. Corresponding angles make an F shape, and corresponding angles are equal, so that A1 and A2 are equal and B1 and B2 are equal. Alternate angles make a Z shape, and C1 and C2 are equal and D1 and D2 are equal. Interior angles add up to 180 degrees, so E1 and E2 add to 180 degrees, and F1 and F2 also total 180 degrees. Okay, let's now put some of what we've learnt so far into practice with a test question. This one's in two parts, and you might like to jot down the details. Kay is drawing shapes on her computer. Part A says she wants to draw this triangle. She needs to know angles A, B and C. We were asked to calculate angles A, B and C. Part B says Kay draws a rhombus. Now we're asked to calculate angles D and E. Notice that the pictures have a not to scale note beside them. This means that they've not been drawn accurately, so you can't measure the angles to find their size. Also notice that the questions ask you to calculate. Calculate angles D and E. Now this means the examiner doesn't want you to draw the pictures to scale and measure them. Instead, he wants you to look at them and then work out the answers using your knowledge of angles. And it's a good idea to show your workings out too. How'd you get on? Well, to hear what the lead chief marker for Key Stage 3 Maths has to say, play on. He's going to take the question from the top.
When you need to find angles in a picture, you always begin by looking at the picture as a whole. The first thing you notice about this picture is the triangle, and you know there are 180 degrees in a triangle. You also see there are no parallel lines, so you won't be looking for corresponding alternate or interior angles. Now look at angle A. There is an angle next to it that lies on the same straight line as A, and that angle is 80 degrees. That means that angle A and the 80 degrees add up to 180 degrees. So A equals 180 degrees minus this 80 degrees, so that's 100 degrees.
Now, angle B.
This angle also lies next to another angle on a straight line. Angle B lies next to 40 degrees on a straight line. So B equals 180 degrees minus 40 degrees, and that's 140 degrees.
Okay, angle C.
Finally, look at angle C in the picture. There is no angle marked next to C on the straight line, nor does it form part of a quarter turn or a complete turn. But if you find this angle here, then you will have an angle next to C on a straight line. Earlier, when looking at the whole picture, this angle here is inside the triangle. The angles in a triangle add up to 180 degrees. You know these angles here, 80 degrees and 40 degrees, so you can find this one by subtracting 80 degrees and 40 degrees from 180 degrees. That's 60 degrees. Now write 60 degrees in here. Now C and the 60 degrees are angles on a straight line, and they add to 180 degrees. So now find C by subtracting the 60 degrees from 180 degrees, and that equals 120 degrees.
Now let's take a look at the diagram in question B.
Looking at the diagram as a whole, you see a rhombus with an extended side here. You know that rhombuses have two pairs of equal angles, here and here, and two pairs of equal and parallel sides. So you may be looking for corresponding, alternate and interior angles.
Okay, let's work through the answer.
You're asked to find angle D first of all. You can see that D sits in a Z shape, along with this 50 degrees here, in between these two parallel lines, here and here. That makes D and the 50 degrees alternate angles, and so they are equal. So D is 50 degrees.
Now for the final angle.
Now E does not appear to be in a Z shape, nor in an F shape of any kind. But E does lie in between these two parallel lines, and these two parallel lines. And here, it lies in between the parallel lines along with angle D, making D and E interior angles. Interior angles add to 180 degrees, so D plus E must be 180 degrees. And as you already know that D is 50 degrees, E is 180 degrees minus 50 degrees, so E is 130 degrees.
Before we leave this unit on angles, let's recap. There are 90 degrees in a right angle. There are 180 degrees on a straight line. And there are 360 degrees in a complete turn. The angles in a triangle total 180 degrees, so angles A, B and C come to 180 degrees. When a line intersects parallel lines called a transversal, then you may see corresponding alternate and interior angles. Corresponding angles make an F shape and are equal. So A1 and A2 are equal, and B1 and B2 are equal. Alternate angles make a Z shape and are equal. So C1 and C2 are equal, and D1 and D2 are equal. And interior angles add up to 180 degrees. So E1 and E2 add to 180 degrees, and F1 and F2 add to 180 degrees too. Right, that's the end of this unit on angles. If there's anything you'd like to go over again, just rewind the tape and play it back. And remember to have a pen and paper handy so you can have a go at the questions yourself. Otherwise, there are always more practice questions and exercises in the Bitesize book and on our website. In this unit, we're going to cover symmetry, congruence and translation. It's not hard, it's just a matter of learning and using the right vocabulary. Let's start with symmetry. Now, reflective symmetry is when something looks exactly the same either side of a central or mirror line. A two-dimensional shape has reflective symmetry if a line can be drawn so that folding the line places one half of the shape exactly over the other half of the shape. Or placing a mirror on that line divides the shape so that the half shape together with the reflection shows the whole shape. This isosceles triangle had one line of symmetry. This rectangle has two lines of symmetry. And this regular hexagon has 6 lines of symmetry. A two-dimensional shape has rotational symmetry if it can be rotated and look exactly the same in a new position. The number of times a shape can be rotated to look the same before fitting back into its original place gives the order of rotational symmetry. This isosceles triangle has rotational symmetry order 1. It doesn't look the same again until it's back in its original place, turning only once. This rectangle has rotational symmetry order 2. It rotates once and looks the same again here and then back in its original place. This regular hexagon has rotational symmetry order 6. It looks the same again here, 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 and here, and then back in its original place, turning 6 times.
Well, when I think about rotational symmetry, I find it easier to put my finger like in the centre of a circle or a square and rotate the page to see how many times the square will fit into itself, and that's rotational symmetry.
With rotational symmetry, I find it easier just to picture it in my head rather than drawing it on a piece of paper, and then just rotate it to each position and see if it fits.
When I do rotational symmetry, I imagine tracing paper over the shape and turning it round through each shape until it goes back to the beginning.
Let's look at some real-life examples of reflective and rotational symmetry. at a railway station.
There are patterns of symmetry everywhere you go. For example, this train station is absolutely full of them. But which of the following shapes are symmetrical? And where are those lines of symmetry?
Wrong. Although these handsome features may seem symmetrical, they are in fact very different, like every other face. If we were to reflect Gideon's left side onto his right side, it would look like this. Not very pleasant. If we were to do it the other way around, it would look even worse.
Even if Gideon was bald, he'd still look odd.
So although something may appear symmetrical, you might have to take a closer look, even if you don't want to.
Now on to congruent shapes. A two-dimensional shape is congruent to another two-dimensional shape if they are both exactly the same shape and size. Two congruent shapes, however, don't necessarily have the same orientation, so two shapes can be congruent if they are the same shape and size after they are rotated or reflected. So for instance, these shapes are congruent to each other. These diamond shapes are congruent because once they are rotated, they're exactly the same and fit precisely over each other. The same with these two triangles and these two T-shapes, which once they're rotated, look exactly the same. However, these two rectangles may look congruent, but look a bit closer. One has longer sides than the other. And finally, let's look at translation. Two-dimensional shapes are translated if they move up or down and left or right, remaining exactly the same size and shape with no rotation or reflection. And the best way to look at it is on graph paper. Let's look at the following triangles that are going to be drawn in this graph to see which are translations of triangle P. Often when using graph paper, we refer to the vertices or corners of a shape and give the corners coordinates to make them easier to locate. So this triangle P has 3 corners or vertices with coordinates 5, 5, 6, 7 and 8, 6. A translation must have the same shape, size and orientation, which means that it stays the same way up. Let's begin with triangle Q. It's the same shape and size as triangle P, but it's rotated through 90 degrees clockwise, so triangle Q is not a translation of triangle P. What about triangle R? It too is the same size and shape as triangle P, but it is a reflection of P in the line y equals 4. So triangle R is not a translation of triangle P either. What about triangle S then? Triangle S is the same shape and size and orientation as triangle P, so it is a translation. In fact, triangle P has been translated 1 square across right and 4 squares down to make triangle S. If we take each corner on triangle P, we can see that this corner has moved 1 across and 4 down. And so has this corner, 1 across and 4 down. And finally, this corner, 1 across and 4 down. Finally, triangle T. It's an enlargement of triangle P, so it can't be a translation. On this graph, shape G has been translated to shape J. Suppose we want to find out how to translate shape G to shape K. Now on the grid, we're told that shape G has been translated to shape J. And we can see that by looking at each corner of shape G, that each one moves 2 squares right and 5 squares down to make the same corner of shape J. Now we've seen how we translate from shape G to shape K. Let's look at this corner on shape G, which becomes this corner on shape K. We must go 1, 2, 3 squares left and 1 square up. Let's check on another corner to make sure we're right. Let's look at this one here on shape G. Move 3 squares left and 1 square up. And it does take us to the same corner on shape K. Okay, that's the basis of symmetry, congruence and translation. For a summary, let's go to the key points. A two-dimensional shape has reflective symmetry if a line can be drawn so that folding the shape at that line places one half of the shape exactly over the other half of the shape. Or placing a mirror on that line divides the shape so that the half shape plus its reflection shows the whole shape. A two-dimensional shape has rotational symmetry if it can be rotated and looks the same in its new position. The number of times a shape can be rotated so it looks the same each time gives the order of rotational symmetry. A two-dimensional shape is congruent to another two-dimensional shape if they are both exactly the same shape and size. A two-dimensional shape is translated if it moves up or down, left or right, and remains exactly the same size, shape and orientation. Right, now that we're armed with these facts, let's tackle a test question. This one has a number of parts to it, so why not jot them down as you go along? An equilateral triangle has 3 lines of symmetry. It has rotational symmetry of order 3. Write the letter of each shape in the correct space in the table below. You may use a mirror or tracing paper to help you. The letters for the first 2 shapes have been written for you. Okay, here's the lead chief marker for Key Stage 3 Maths, who's going to take us through the question from the top. First, he's going to look at the examples to understand the question fully.
Look at shape A first, the equilateral triangle. You can draw a line here and fold it so this half of the shape fits exactly over the other half of the shape. You can also draw a line here so that this half of the shape fits exactly over this half of the shape. And finally, you can draw a line here so that this half of the shape fits exactly over this half of the shape. There's no more lines you can draw to mark reflective symmetry. So the equilateral triangle has 3 lines of symmetry. If you rotate the equilateral triangle, it looks the same again here. That's once. And then here. That's twice. Then back in its original place, making 3 times in all. This means the order of rotational symmetry of an equilateral triangle is 3. So shape A is written as having 3 lines of symmetry and order of rotational symmetry 3. Look at shape B now, the parallelogram. There is no line we can draw so that one half of the shape will fold exactly onto another half of the shape. That line doesn't work. Nor does that one. Nor that one. A parallelogram has no line of symmetry. If you rotate the parallelogram, it looks the same again here, then back in its original place, making twice in all. So shape B is written as having no line of symmetry and order of rotational symmetry 2.
Now, if you're not sure about the answer so far, have another look before moving on to the rest of the question.
Shape C is a rectangle. There are 2 lines you can draw so that one half of the shape will fold exactly onto another half of the shape, a horizontal line and a vertical line. Shape C has 2 lines of symmetry. If you rotate the rectangle, it looks the same again here, then back in its original place, making twice in all. So the order of rotational symmetry of a rectangle is 2. Write C in a box under 2 on number of lines of symmetry, and a box across from 2 on order of rotational symmetry. So that's here.
Now for shape D.
For shape D, there are no lines of symmetry you can draw so that one half of the shape will fold exactly onto another half of the shape. It may look as though there is a line here, but it doesn't work. Look. Nor does it work here. Nor here. Shape D has no lines of symmetry. If you rotate shape D, it looks the same again here. That's 1. Then here, that's 2. And then back in its original place, making 3 times. So order of rotational symmetry of shape D is 3. Write D in a box under 0 on number of lines of symmetry, and a box across from 3 on order of rotational symmetry. So that's here.
Right, what about shape E?
For shape E, there are no lines of symmetry you can draw so that one half of the shape will fold exactly onto another half of the shape. So shape E has no lines of symmetry. If you rotate shape E, it does not look the same again until it's back in its original place. So the order of rotational symmetry of a shape E is 1. Write E in a box under 0 on the number of lines of symmetry, and a box across from 1 on order of rotational symmetry. So that's here.
And shape F?
Finally, shape F. There is one horizontal line of symmetry you can draw so that one half of the shape will fold exactly onto another half of the shape, but no other lines of symmetry. Shape F has one line of symmetry. Rotate shape F, and it does not look the same again until here, back in its original place. So order of rotational symmetry of shape F is 1. Write F in a box under 1 on number of lines of symmetry, and a box across from 1 on order of rotational symmetry. That's here. So the final box will look like this.
So, how did you get on? Well, if any of your answers didn't match with ours, you can always rewind the tape and go through it again. That's it for this unit on symmetry, congruence and translation. And remember, there are more examples and questions for you to work through in the book and on our website. You can check them out now or move on to the next unit. Okay, let's round off with 2-dimensional shapes and 3-dimensional solids, starting with 2-dimensional shapes. 2-dimensional shapes appear flat on a piece of paper like these, but 3-dimensional solids appear to rise out of a piece of paper like these. And it's much easier drawing a 3-dimensional solid if you use isometric paper. That's triangular dotty paper. For example, this cereal box, which is a cuboid, can be drawn like this. And this chocolate bar, which is a triangular prism, can be drawn like this. When drawing any shape that's slightly tricky, it often helps to first draw a box that the shape could fit into. This can help get the shape into perspective. So when drawing this triangular prism, for instance, it's a good idea to first draw a cuboid roughly the same size as the prism. And this hat box, called a hexagonal prism, can be drawn like this. Once again, drawing a cuboid of a similar size first helps to get the hat box into perspective. Why don't you try and find some isometric paper yourself and then have a go at this test question. Four cubes join to make an L shape. The diagram shows the L shape after quarter turns in one direction. On your piece of paper, draw the L shape after the next quarter turn in the same direction. So, how did you get on? Well, let's check through the answer.
Let's look at the L shape turning from its beginning position here, where it lies on its 3-cube side. Imagine it moving through a quarter turn, like this. Now it stands up to make the L shape the right way up. Imagine it moving through another quarter turn, like this. Now it lies on its 1-cube side. Now imagine it moving through another quarter turn. Now it stands as an L shape upside down, like this. When drawing on isometric or triangular dotty paper, always work out how your shape is going to sit. Notice that all the cubes lie in this diagonal line here. So you have to draw the base of the cube on the same diagonal line as the base of the cubes in all the other shapes. The cubes also lie on these diagonal lines here. So draw the cube lying on this diagonal too. Imagine the L shape upside down. You need to draw 3 cubes in a column. 1, 2, 3. Finally, the single cube lies on the same diagonal, to the left of the column of 3 cubes there.
Now let's look at some more facts about three-dimensional solids. Some three-dimensional solids have flat or two-dimensional faces. This triangular prism has 2 faces that are triangles and 3 faces that are rectangles. Looking at it from the front, called the front elevation, we see a triangular face, and looking at it from the side, called the side elevation, we see a rectangular face. If we look at it from above, we see the top elevation, a rectangular face with a line through the centre of it. Now let's look at this hexagonal prism. It has 2 hexagonal faces and 6 rectangular faces. The front elevation is a rectangle, the side elevation is also a rectangle, and the top elevation is a hexagon. Okay, now time for another test question. The diagram shows a model made with 9 cubes. 5 of the cubes are grey. The other 4 cubes are white. Part A. The drawings below show the 4 side views of the model. Which side view does each drawing show? Part B. Complete the top view of the model by shading the squares which are grey. And C. Imagine you turn the model upside down. What will the new top view of the model look like? Complete the new top view of the model by shading the squares which are grey. Pause the tape, look at the drawings carefully and decide which side view is which. So, how did you get on there? Well, let's work through the answers with the lead chief marker for maths. And as always, he'll take each part one at a time.
Notice that this drawing is an F shape. So it is not side view A or side view C, as they are definitely not F shapes. It has a white square in the corner here at the top and a grey square next to it, so it suggests it is side view B. This drawing is side view A or side view C. it has a grey square and a white square at the top, so it must be side view A. This drawing is another F shape, so it must be side view D. That means that this drawing must be side view C.
OK, on to part B.
Part B asks you to complete the top view of the model by shading the squares which are grey. Did you decide on these squares?
OK, now for the final part. And you might want to pause the tape while you think about the answer.
Finally, Part C says, imagine you turn the model upside down. What will the new top view of the model look like? Did you decide on these squares?
Finally, it's worth remembering that to make a three-dimensional solid, you have to draw a two-dimensional drawing first. These drawings are called nets, and here's what I mean. If we take a dice, for example, and we open up all of the sides so that it becomes a flat surface, it would look like this. Or this. Or this. Right, before we go any further, let's hear from some other students about how they tackle net shapes.
When I'm thinking about net shapes, I think what sides are connected to where, and then once I've done that, I think about how many sides there are, and then I think about how it would come together to make the final object.
With net shapes, what you need to remember is that you need a central shape, which is the base of your shape, and then all the sides are connected to it, so that if you were to pull the shape up, it would join to make that particular shape.
Top tips for working out the net of a shape is to imagine that the shape that you're trying to work out is a hollow. Then you can try and unfold the shape onto a piece of paper. Then you should be left with, say if it's a cube, then you should be left with a T. But mainly, imagine the shape is hollow and trying to sort of unfold it onto a piece of paper. That should help you.
Right, let's recap. Two-dimensional shapes appear flat on a piece of paper. Three-dimensional solids appear to rise out of a piece of paper. Three-dimensional solids have two-dimensional faces. Three-dimensional solids have different two-dimensional faces when viewed from the top, front or side, known as the top, front or side elevations. To make a three-dimensional solid, a two-dimensional plan has to be drawn. These plans are called nets. Right, armed with all that information, let's go to another test question. The top and the base of this box are semicircles. One of the nets below could fold up to make a box like this. Put a tick on the correct net. Right, now let's look at the answer with the lead chief marker.
As the box unfolds, you can see that the second row down and on the left of the page is the correct net. To be sure it is the correct net, check which side would glue to which other side in order to make the box up again. This length would fit along the circumference of the arc of the semicircle, here, as would this length fit along the arc of this semicircle here, while this length here would fit with this length here.
Well, that's it for this unit and for this programme. Remember, there's more information, practice questions and exercises for you to try out in our book and on our website. And don't forget to build in a break to your revision schedule.
Details of all BBC Learning Zone programmes can be found on CFAX pages 630 to 635.
You're watching BBC Learning Zone as we bring you the second of the maths revision programmes from GCSE Bitesize.
Hello and welcome to GCSE Bitesize. This programme will help you with your GCSE maths exams. It focuses on what you need to know about algebra. There are two other programmes about numbers and measures and shape, space and data handling. The best way to revise with Bitesize is to tackle one topic at a time, working through the video in bite-sized chunks. Each programme is full of useful information with sample questions for you to try. And there's more in the GCSE Bitesize books and on the GCSE Bitesize website at www.bbc.co.uk/revision. There are several exam boards, but the questions will be very similar. Papers are set at 3 levels or tiers by all the boards. If you do the foundation paper, you can achieve from grade G to D. Intermediate covers grades E to B, and higher grades C to A star. Your teacher should have discussed with you which paper you're aiming for. During the programme, we'll add icons to show you which level we're aiming at. This algebra programme is divided into 2 main sections: algebraic methods and sequences, graphs and loci. First, let's look at algebraic methods.